Anyone has a question regarding any of the stuff that we have been discussing on kinematics? If you have any question or comments or whatever, feel free to let me know. I think the semester is going to end up around in 20 days from now, and we are going to be done with this chapter like next Monday, and we're going to start the last chapter next week, which is chapter 17. Okay. So let us start. If we got disconnected, you can always log back into this room, and I'm going to start the recording session right now. Just a second. Okay. Okay, guys. So I'm going to start by solving this problem that you have here that is being shared, and so in this problem, basically, we have this link, and we have this quarter of a circle, and y basically is decreasing as a result of this velocity. So point A has a velocity, downward velocity, and we would like to find the angular velocity of the link accordingly. All right. So in this problem, basically, we need to find this theta. This is more like a mathematical problem. So I'm gonna stop sharing so you can see what I have here. Is so this is what we have is we have this guy over here, and I'm gonna draw it like that, and we have this, quarter of a circle, and we know the distance from here to here is given to you as y, and we know that this guy will always be perpendicular, right? Because a tangent with a circle will always be perpendicular with the center, and this guy is theta. We know this guy is going to be r. So I would like to find essentially theta prime as a function of y prime, maybe y double dot, etc. How do I calculate that? How do I find that? So here it's basically this is geometry primarily, and what we can say is we can say y, right? Y times sine theta is going to be equal to r, right? And you guys can open up this. So I'm going to share back my screen so I can show it to you clearly here. So here, what I mean by that is, y, right, multiplied by sine theta is going to be equal to r. Okay, so we can use that relationship to develop this further. So y sine theta is going to be equal to r. Okay, and now if I differentiate the left and the right side of this, I should be able to get theta prime as a function of y prime or etc. Okay, so what is the derivative of r? Can anyone tell me?
It's 0, no?
Yes, exactly. The derivative of r is 0. So, so on the right, I'm gonna have here 0. So it's gonna be. How about on the left? On the left, I'm gonna have y prime, right, times sine theta plus y. Derivative of sine theta is equal to what? Cosine theta multiplied by theta prime. is equal to 0, right? And how is by the way y or y prime related to the velocity of the object? We said the velocity of the object is downward, right? So if VA is positive, how is VA related to y? I think VA is equal to minus y prime, right? Because if VA is positive, right, y prime is being reduced, right? So this is what I mean by that. So positive velocity mean you have y prime is going to be negative. Okay, so here I could, or you can continue writing it like that. So theta prime is going to be equal to what? Minus y prime sine theta divided by y cosine theta, which is equal to minus y prime over y multiplied by tangent theta. So now let us see if this actually makes sense. So if y prime is negative, right? If the value of this term y prime is negative, it means that the variable y is decreasing in time. So as time progresses, y is going down, right? So this guy is negative. Negative times negative is positive, right? So y prime over y is positive, tangent theta is obviously positive, so theta prime will be positive. So if the bar, or if y is going down, then theta is doing what? Is opening up, right? Theta is increasing, which makes sense, right? So I could also even replace this minus y prime by VA. So if the object has positive velocity, it means that theta prime is going to be increasing. So this allows you to relate the velocity of point A with theta prime, which is the angular velocity of this rod, right? And then I'm drawing this rod as a straight line. Okay, any questions on that? Okay, now next step is we would like to find the acceleration, or the angular acceleration of the bar, which is basically theta double dot. How can I find the angular acceleration of the bar? Any comments?
Derivative.
Exactly. You differentiate this line, right? You can differentiate this line, and then you're going to get to the double dot, right? So I'm going to rewrite this one more time. So we had y prime sine theta plus y cosine theta times theta prime is equal to 0. Differentiating this, you're going to end up with y double dot sine theta plus y prime cosine theta theta prime plus y prime cosine theta theta prime plus y. So this is a chain rule. You start by differentiating this guy plus y. Derivative of cosine theta is minus sine theta theta prime times theta prime plus y cosine theta theta double dot is equal to 0. Okay, so they tell you that the point A has no acceleration. It means that y double dot is equal to 0. It means the first term is 0, and these two will actually add up. Y prime cosine theta theta prime plus y prime cosine theta theta prime will actually add up. So you end up with 2 y prime cosine theta times theta prime, and then if you can recognize, this is like the Coriolis, right? And ironically, when you are developing the accelerations, etc., you will always see these terms actually come up. We remember y prime, like linear velocity times angular velocity times 2. This is like some type of a Coriolis acceleration. So this and that, and then plus y theta prime squared times minus sine theta. So this guy is going to be minus plus y cosine theta theta double dot is equal to 0. And then this is like the centrifugal acceleration, right? You guys agree? Y theta prime squared, like distance times theta prime squared. So from here you can get theta double dot. So theta double dot is going to be equal to y theta prime squared sine theta minus 2 y prime cosine theta theta prime, divide that by y cosine theta. And this is the angular acceleration of the rod. So now I could take this problem, and then I could ask you, as a result of this theta double dot, what is the acceleration of any point on this bar? And let me ask you guys this question. If I, on the exam, if I ask you, like, based on these, what is the acceleration of this point? How do you do that? If I ask you, what is the acceleration of this point? A point, obviously, not like that, just a point. How do you get this acceleration? Can anyone tell me? Can anyone tell me how do I get the acceleration of this point? Take a guess. It's totally fine to be incorrect. Let's just do an exercise. How would you do this? Like if I ask you to find the acceleration of this point, or let's start by finding the velocity of this point. How do you find the velocity of this point?
We use the formula.
Okay, how do you apply the formula?
Related to the point A because its velocity is 0.
Velocity of point A is 0.
It's not moving.
No, point A has a velocity.
No, we have VA. We just use VB equal VA plus omega cross RAB.
Exactly. So you have the velocity of, they have point A, right? And then you're trying to find the velocity of B. So here we find omega, right? And then you know omega is going to look like that, right? So we can, obviously, the first thing that you have to do is you want to put a frame, IJ, right? Do you guys see when I'm writing here, is it big enough or?
Yes.
Okay. All right. So you have IJ frame, right? And then we know point A has a velocity like that, right? So this is the velocity of A. This is given to us, right? So we say VB is equal to VA as a vector, right? Plus omega, which is now theta prime K, right? Cross RB with respect to A, right? This is what I need to do. What is VA in this case? It is minus VA times J, right? Because VA is in the opposite direction as the J vector. How about omega? Can someone tell me what is omega in this case based on, you know, not this, this is alpha, but what would be omega? What is omega in this expression? Can someone tell me?
Plus omega K.
Omega, okay, so, you know, theta prime is like that, right? So this guy is rotating like this, right? So if this is I, J, and then so K has to be positive. So this is positive K, right? So in this case, omega has to be minus theta prime K. Do you guys agree why it is minus theta prime K? Right? So this is I, J, K is actually coming up, right? So this rotation will give you positive K. In this case, this guy is rotating the opposite direction, so K is downward, right? So based on this omega, it is in a negative K direction based on this frame that I have. Does it make sense? Okay. So if omega was like this, then K would be positive. So this is minus theta prime K. How about RBA? So RBA is the vector from A to B, right? If the length of this arc is L, and let's say this angle here is, you know, well, we actually have this angle theta right here, right? What would be RBA in this case? So in the I direction, it is minus, right? So minus L sine theta. How about in the J direction? It is also minus L cosine theta J. Okay, and then this is what you have to do. Okay, just continue this expression from here, and then you can find the velocity. And then in a similar approach, you can find the acceleration of point B as well. Why? Because you also have alpha. So this is very important that you recognize that the angular velocity is a vector, and you use the right-hand rule to determine the direction of this angular velocity vector. Okay, so that is this for this problem. Let's continue with another problem right now, and I'm going to jump to example 4. So let me share this, and then this is example 4. What we have over here is we have this wheel, and that wheel is rolling. So this is your wheel, and the wheel is rolling, and then this guy is hinged, right? And then this angle right here is theta, and then the wheel has a radius of r. And they also tell us that the wheel has a velocity of v coming to in this direction, or VO, right? Point O has a velocity VO. Okay, obviously it's translating, so no matter what I put this vector, but I'm gonna actually put it here just so we stay consistent. Okay, this is VO. And you're trying to find theta of this. How do you find theta, or you know, the angular velocity of this bar as a function of these equations or these mathematical relationships? Can someone, you know, think about it, and then maybe how do you get that? I need to get theta, right? Theta prime is a function of the velocity of point O, maybe R, right? Maybe acceleration of point O. We don't know, right? How do you find theta prime here? I think one of the easiest way of doing that is some people can say, you know, diameter. Can I say like, you know, if that distance here is x, okay, can I say like, you know, diameter, right? This diameter, right? Or can I say like, you know, tangent theta is d over opposite over adjacent d over x? Is that correct or no? Can I say tangent theta is equal to the diameter divided by x, where x is that distance? I'm just gonna redraw this very quickly, so because can I say like tangent theta is equal to d over x? Is that true or no?
Yes, it is.
It is. I think not quite. Why? Because, you know, the radius has to be perpendicular over here, and then it's actually perpendicular over here, right? It's not up. It is in that direction. The tangent will actually look like that. So you cannot say tangent theta is equal to d over x. You actually have to say tangent theta over 2, right? So tangent theta over 2 is actually equal to the radius, right? Opposite divided by the adjacent, so r over x. So r is equal to x multiplied by tangent theta over 2. This is the correct relationship. Okay, so on the exam, just be careful about those. You know, you cannot say d, because this point d actually will not actually, cannot relate theta, right? So if you are talking about this, you're finding the angular velocity of this line, which is crossing through the top of the cylinder, and that top of the cylinder doesn't actually touch this bar, right? You can think about it when, if, you know, take like extreme positions, right? If the circle is very close to the hinge, what happens? So if that guy is here, right, then this is what you're doing here, right? And this is theta. In that case, you can't say that, you know, if this distance is x, you know, this is not changing. Here, obviously, you cannot say tangent theta is equal to d over x. Well, you could definitely say it, right? You could always make mistakes, but how do you know that you've actually made a mistake? Let's say you try to actually do this. Essentially, you would be finding the angular velocity of this virtual line, right? Which is not the actual correct angular velocity of this rod, right? We need to find the angular velocity of this rod, and what we can do is we can always say that this is always correct. So if this guy is theta over 2, right, where theta is indeed the angle of the rod, then tangent of theta over 2 is going to be equal to the radius of the disk divided by x. So r is going to be equal to x times tangent theta over 2, right? And now we can, like, you know, differentiate these, and differentiating the radius is going to be what? 0, right? So 0 is going to be equal to x prime tangent theta plus x, derivative of tangent theta over 2, you all know, 1 plus tangent square theta over 2 multiplied by theta prime over 2, right? And we need this angular velocity, right? So how do I do that? So I'm gonna say bring this to the side, minus x prime tangent theta over 2 is equal to x 1 plus tangent square theta over 2 times theta prime over 2. So theta prime is equal to minus 2x prime tangent theta over 2 and then divided by x 1 plus tangent square theta over 2. Let us see if we can do like, you know, some simplifications over here. What would you end up with? So minus 2x prime tangent theta over 2 x. So, you know, this guy is going to be sine over cosine, right? So it would be what? Cosine square theta over 2 plus cosine square plus sine, sorry, sine square theta over 2 divided by, right? I'm using cosine square theta, right? Because I can always say this guy is equal to sine square theta over 2 divided by cosine square 2. So this guy is going to be 1, right? And here minus 2 x. So cosine square over 2, I'm going to put it on top, cosine square theta over 2. And this guy is going to be equal to minus 2 x prime over x. So sine over cosine multiplied by cosine, right? Cosine square. So I'm going to take cosine from here, right? And then I'm going to take this 2 on top. And I have minus 2 sine times cosine. It's going to be equal to what? What is minus 2 sine? This is theta over 2 here, obviously.
Cosine to alpha.
Cosine to, exactly. So minus x prime over x sine, right? Sine 2 theta over 2 is going to be sine theta, right? So this is your theta prime. Okay, does it make sense, guys? So theta prime is equal to minus x prime over x. If the wheel is actually approaching, then x prime is negative or positive. If the wheel is coming to the left, what would be x prime? Would be negative or positive? Negative. So negative times negative is positive, right? Then theta prime is going to be increasing or decreasing?
Increasing.
Increasing, right? Which makes sense, right? So this is, you know, the beauty about, you know, dynamics is, you know, it all makes sense, right? Once you express your mechanical system correctly, then it should all make sense, right? So now if you want to get the angular acceleration of a theta prime, how do you get the angular acceleration of the bar? Want to differentiate this one more time, right? So we're going to end up with theta prime x minus x prime sine theta. Differentiate one more time. So theta double dot times x plus theta prime x prime minus x prime cosine theta times theta prime, right? So theta double dot is going to be equal to what? Minus x double dot sine theta minus x prime cosine theta times theta prime, and then this whole thing is divided by x, and then we still have minus theta prime x prime. Now we can obviously take this theta prime and then plug this back in here and then simplify it further, but this is going to be what you have. Okay, any questions, guys, on this problem, or are we good? Okay, so okay, next problem. I'm not gonna. This is a 4-bar linkage, so we'll revisit that later. This is not. We're not gonna be actually covering that in this course, but we'll cover some other problems. So you know, does anyone know what is this? For example, what is this called? This guy, this component, this wheel. Does anyone know what is it called? Okay, so this large wheel is actually called a flywheel. Okay, and flywheels are used, for example, in the combustion engine, right, or in the piston. So this is a piston, right? This is actually like an engine, right? This could be like a steam engine, right? And does anyone, if you actually Google this guy here, right? This is actually used to control the velocity of this guy. So this was actually used on trains to control the velocities of trains. So when the engine basically is ramping up, right? You have these guys begin to rotate, and then the centrifugal acceleration will cause these two bolts to basically lift up. And as they are lifting up, they allow actually more air to come into the engine. Okay, I'm talking about this component. That one. But however, what we're looking to analyze here is basically what is actually happening here. So this is a flywheel, and then the flywheel basically stores energy, and then to keep this engine going, right? Sometimes some strokes don't have enough energy to keep that thing going, and then you just charge this basically in energy. What we would like to do here is we'd like to find the velocities of the various points over here. So this point A is on a piston, so point A is going to be translating. The velocity of point A is going to be like that, right? And point C has 0 velocity, and each rigid body is going to have an angular velocity over here. All right. So if I tell you that point A is translating, right, and if I tell you so if point A is translating and point C has a 0 velocity, right? Can I find, for example, the velocity? Or if I tell you, let's say, if I tell you the velocity of point B, right? It looks the way it looks right now. Can you find the velocity of any other points on here? On this link, for example? Right? So what you have to do here is obviously you have to count the number of rigid bodies, right? So this is one link. We have the velocity of point A is going to be horizontal, and then the velocity of point B is going to be like that. Now you can use these two velocities, or you can actually use one velocity to find the angular velocity on that rigid body. Here's what I want to show you guys. I want to show you something very important and then also very interesting at the same time. If you actually have a rigid body, okay, if you have any random rigid body, right, and let's take just 2 points on that rigid body. If I actually have point A, let's call them point A. Let's say, obviously, point A is going to have some velocity, and then point B could have this velocity, right? So the equation that we have tells us that the velocity of B, let's say, is equal to the velocity of A plus omega cross RB with respect to A, right? If I have the velocity of A and I have the angular velocity of the rigid body, it means I can find the velocity of B, right? But let's say if I actually have the velocity of A and I have the velocity of B, what else can I find? What can you find? Exactly, you can find omega, exactly. So if you actually have the velocities of 2 points, you can actually find the angular velocity of that rigid body, right? And by the way, this equation is actually, how many equations are these? Like this thing, how many equations is that? This is actually 2 equations, right? The reason why it's 2 equations is because you have I and then J, right? So you can write this equation in the I direction, and then you can also write this equation in the J direction, right? And you can actually use this to solve the system, and then you should be able to solve omega, or the velocity of A, etc. The best way to do this is, let's do an example on this, and I'm gonna work on this problem. You guys see this problem? Example 6. Okay, and this example, what we have is we have this link AB, we have link BC, and then we have this link. How many rigid bodies do I have in total in this example?
Three.
You have three, exactly. You have AB, BC, and you have this block, right? So the block is translating. This link is, translating and rotating, and then that link is only rotating, right? But it doesn't really matter. What we should know is each link here have an omega, except this guy, right? This block has no omega because if you draw a line on it, it's not rotating anywhere. So this is simply translating. So in this problem, basically, they gave you the velocity of point of the block is equal to 8 meters per second in that direction, and would actually like to find the angular velocities of link AB and then link BC. How could you do that? So I'm going to stop this, right? So we have a link like that, right? And then we have, this is another link, right? And what we have here is, this is point A, point B, and then point C. And we know this distance from here to here is 2 meters. And then from here to here is 2 meters. And we know point C is actually going down with this velocity of 8 meters per second. And this angle right there is like 45 degrees. Okay, I need to find the omega of AB and then omega of BC. So what I have to do first is I have to draw a frame, right? IJ frame. All right, and here's what I could do, right? I have, I'm gonna call this omega AB, and this guy has omega BC, right? And then we're gonna assume all are in the positive K direction, unless they prove themselves no. So what I can do is, this is a rigid body, so I can say the velocity of B is equal to the velocity of A plus omega AB cross RB as viewed from A. Right? Why? Because I'm taking this whole thing as one rigid body, and then I can say the velocity of point C is equal to the velocity of point B plus omega BC cross RC as viewed from B. Right? You guys agree?
ساعتها بعمل link مع A و C.
Exactly. Then you can link them up. Exactly. But one thing here, I shouldn't say, I should basically write VB again, right? I shouldn't use VC. I'm going to say VB is equal to, so I find the velocity of B with respect to A and velocity of B with respect to C, right? And then I make them equal, right? So here VB as from A, and then VB is equal to VC, right? Plus omega BC cross RB as viewed from C, right? The velocity of A is equal to how much?
Zero.
Zero,
Zero.
exactly, right? So I'm gonna say omega AB cross RBA, like this is equation 1, equation 2 is gonna be equal to this, right? VC plus omega BC cross RBC. Okay, how many equations do I have here in this rectangular frame? How many equations do I have?
Two.
2 equations, right? How many unknowns?
كمان 2.
Which are?
Omega وأوميجا.
Omega AB and omega BC, exactly. So, okay, so this is very important. So we have 2 equations and then 2 unknowns. We can actually solve the angular velocities of the two bars. What is a omega AB in this case? We don't know, right? But we're gonna assume omega AB is in a positive K direction, right? Okay, so omega AB K, right? So I'm gonna put a vector on it. Cross, what is RB with respect to A?
minus 2i.
Is it minus 2i? I think it is 2i, right? B as viewed from A, right? So it is a vector pointing toward B, right? RB as viewed from A, right, is a vector pointing from A to B, right? And then I have this is my I, right? So RBA is equal to 2i. How about VC? Can someone tell me what is VC?
It's 8 cosine 45.
Okay, so in the I direction, A square root of 2 over 2 I ما هيك. In the J minus ما هيك.
Yes.
Okay, plus omega BC cross that. So we don't know omega BC, so I'm gonna just keep it like that. Omega BC K cross. What is RB as viewed from C?
2J.
2J.
2J. Okay, guys. So the session will end in 2 minutes. So I'm gonna stop this, and then you guys will log back in. Okay, I'm gonna stop this recording, and I'm gonna merge them later. So log back in after I close now. Okay, guys. So how do I go from here? Okay, I think. Okay, guys. So this is what I have. So we were here. Omega BCK. So here, you know, when you are solving the angular velocities, obviously you don't know their directions, right? So here you just assume they are in a positive k direction, meaning they are like that, right? And then if ultimately you find omega AB to be opposite, or you get it negative, then it is opposite to the direction that you assumed. Okay, this is what I have. Okay, so let's go from here. So I'm gonna write this on a new sheet again. So we have. Right, so we have these two links, and we have omega AB, and then we had omega BC, right? We assumed this guy was like that, and then this guy was like that, right? And then point A, B, and then C. And then ultimately we had omega AB K cross 2I was equal to 8 square root of 2 over 2, which is cosine 45 degree in the I direction, because BC was like that, minus 8 square root over 2I plus omega BC K cross 2J. So I need to expand that. So what is K cross I? Just apply the formula, right? IJK, IJK. So K cross I, I'm going to be going positive, is going to be J, right? So 2 omega AB J, right? K cross I is J. So it's right, equal to 8 square root of 2 over 2I minus 8 square root of 2 over 2I. We still have omega BC K cross 2J. K cross J is minus I, right? So minus 2 omega BCI, right?
Doctor,
Yes.
isn't it minus 8 square root of 2 over 2J?
Which one?
Yes, the negative one.
This one?
Yes.
Yes, you're right. This is J. This is J, right? Yeah, it is minus J direction, right? Thank you. Yes, very good. Okay, so هنا عندنا basically J is going to be equal to J, right? So 2 omega AB has to be equal to this guy, right? Minus 8 square root over 2 over 2, right? So omega AB is going to be equal to, so 8 over 4 is going to be equal to 2, minus 2 radian per second. Okay, so omega AB is going to be minus. So we got omega AB. How do I get omega BC? So here, this guy has to be 0. Okay? So the I components has to be 0. So 8 square root over 2 over 2. So 0 is going to be this guy, right? Minus 2 omega BC, right? So omega BC is going to be equal to, again, 2 radian per second. So this guy is going to be positive. And do you guys see how I have this? Why is this true? Right? So here what you are doing is simply, you can separate the J and the I components, but I'm doing it, you know. So the J is going to be equal to the J component, right? So 2 omega AB is going to be equal to minus 8 square root of 2 over 2. So you can solve omega AB is going to be equal to minus 8 divided by square root over 2 divided by 4, right? 8 over 4 is going to be equal to 2. So we got that. So this is correct. And then the last thing is you're going to make the i's are equal. So, you know, so 8 square root over 2, square root of 2 over 2 minus 2 omega BC is going to be equal to 0, right? So omega BC is going to be equal to 8 square root over 2, square root of 2 over 2 divided by 2, which is positive, right? Does it make sense or no? So if I'm actually putting this guy, this line is gonna like sort of like, you know, open up like that, and then this line is gonna open down like in the other way, right? So omega AB is actually opposite to what we assumed, right? Does it make sense or no? So as I'm basically pulling this guy down, right? So this line is gonna be rotating like this, right? I assumed omega AB is like that. So here we actually know that omega AB is equal to minus 2 square root of 2 radian per second, which makes sense. How about omega BC? Is it going to be positive or negative? Omega BC is positive, right? And it makes sense, right? If I'm basically pulling on this line like that, basically this is going to like, you know, sort of do this, right? So if it's doing that, then this guy is going to have negative angular velocity, and then this guy is going to have a positive angular velocity. All right, guys, is that clear, or are we good? This line is
Doctor,
yes.
هون قالوا لنا انه find it at a given instant بس حسوب قال لنا in general كيف بعرف كيف RBA و RBC بيتغيروا؟
Okay, this is a very good question. Here's how you know. Well, basically, depending on what is happening, if the velocity of point C is actually constant, right? What you actually have to do is you actually have to find alpha. So based on this velocity, you can actually find alpha in a similar manner, right? You can find alpha of omega, alpha of AB, and then alpha of BC, and you actually have to integrate them. You integrate them, and then every time you integrate, you basically solve for omega. So this is beyond what we're doing, but you actually have to do it numerically, like in MATLAB or something like that. This is how you can solve them as a function of time. So obviously, you know, theta, right, is going to be integration of omega dt, right, from 0 to some time t. Here, what we did is we obtained omegas, right, at that particular instant, meaning for this particular geometry, right? And we assumed here VC is constant, right? So if theta changes, right, here we assumed R to be 2I. Like we assume this guy was what? RBA, right? So RBA is going to be changing. So you would have to, so every time you solve this, right, you have to update the positions of B and C. So you solve this, you know, in the loop, and then you basically find where this point is going to be. Okay, what I'd like to do actually is at some point after we're done, I'm actually going to do like, you know, a session on MATLAB or Python, and I'm gonna show you guys how simple it is to implement what we're doing in this course, and then to basically really visualize basically the, you know, the software will basically plot this, and then you'll see basically as a result of this velocity what actually happens. And then actually go one more step, and we'd actually put the weight. So we can put the weight of this link and then the weight of this link, and then you let go, and then you see that how that will actually fall. And all that can be done numerically, but like I said, what you have to do is, let's say here you solved omega, right? You would actually have to, you know, numerically integrate that, find theta, which is integration of omega. So at every step, basically, you increase your angle by a little bit, right? So basically, this integration is going to look like that. So theta is going to be equal to omega times dt, simply, right? Plus the old omega, right? So this is iteration I plus 1, this is at iteration I, and this is at iteration. So you have this like in a loop, and then every time you multiply omega by dt, and then you get your new angle. But once you get that new angle, you're gonna update this new vector, where this vector is. And then from here, you find a new omega, you plug it here, you find a new theta, you come back, you find r. So you do that in a loop. Does that make sense?
Yes, thank you.
Okay, so let's solve one last problem, and or actually I think time is up, so it's a 50-minute session, so I think this is good for today. I'll see you guys on Wednesday. Okay, and if you have any questions regarding the exam on Friday, like I said, the exam is going to cover chapters 14 and 15, which are impulses, right, and then energy. So make sure you are very familiar with energy. Make sure there are several problems that you should be very familiar with, right? Using the energy, how the energy is conserved. Remember this problem that we did in class, right? We had like a spring, right? And then pushing a ball, right? We find a position where n is 0, remember? mg, and then here we put this guy is going to be equal to mv squared over r, right? So make sure you are familiar with that. There is one problem which is also very important that looks like that. And basically you have something on a sphere, and this guy will actually slide, and at some angle, I'm going to ask you to find the angle where this guy actually, begins to lift off this guy, right? There is a problem like that in the homework, so make sure you also solve that. Okay, with friction, like let's say you also have friction here, right? Mu times n. This is initial state 1, and then at that state 2, let's say you also have friction. How do you find the velocity of this guy when it's here? And you have friction, so you have to take into account that here the normal is changing, right? This is your mg is always vertical, so just make sure you solve this problem. Okay, so make sure you solve this problem. Make sure you are very familiar with energy. Make sure you are familiar with impulses. If I have an impulse problem, how do you solve it? Okay, so just spend some time to work on these. Okay, guys, any more questions on here or regarding the exam?
We will have a true or false question like the first one.
Yes, you will have true or false problems. And guys, I want to tell you one thing. So regarding the exam, your grade will actually be published the next day. Okay, not just after the exam, because I may change some stuff during the exam because students were taking other their friends' answer. So just give your best answer to the problem, regardless of what actually happens, and then we actually solve the problem, and then make sure you guys have the right solution. After we are done with the exam. So, like I said, this is important. Okay. Yeah, sure. Maroon, you have a question regarding the coefficient of restitution. Is it like taking values as vector? So the coefficient of restitution, the coefficient
vectors ولا value تبعه.
Okay, so in the case of the coefficient of restitution, you always have to apply it along the line of action. And there is a very important problem that you guys have to be very familiar with, which is the ramp and the ball problem. Make sure you really solve this problem. Like, when the ball falls, what happens to the ramp? What is the velocity of the ramp after the impact? And this problem, basically, you have to apply the coefficient of restitution along the line of action, right? So you're taking the velocity of this guy, right? So this velocity vector, right? It has this component, okay? So this component is the one that you're using when you are applying the coefficient of restitution, right? And this guy has this velocity. You are going to take this component of this velocity vector projected on the line of action, right? So you're always taking these. So let's say this is ball A, it has VA1, and then ball B has VB1, right? What is the definition of the coefficient of restitution? We said E is going to be equal to what? VB2 minus VA2 divided by VA1 minus VB1. Okay? And this only applies along the line of action, right? So obviously here, if VA1 is greater than VB1, right? So this guy would basically reach it. Otherwise, this guy the collision would never occur. So VA1 is greater than VB1, so this guy is positive, right? So from here, we can find the relationship between VB2 minus VA2. So VB2 minus VA2 is going to be equal to VA1 minus VB1, right? Assuming we have the initial velocities. Obviously, this is not enough, right? We need one more equation, which is the momentum equation here, right? And from the momentum equation, we can get the rest. Okay, but remember, always the coefficient of restitution always applies along the line of impact.
بتاني example كيف نقيت line of action؟
Here? Here? In this
Yes, the one with the ball falling. Yes.
Okay, how can someone tell us how did I get this? Okay,
مش
just
دايما perpendicular على surface.
perpendicular to the, exactly, yes, perpendicular to the surface or the tangent, right, to be more accurate. Perpendicular to the tangent. When this ball basically hits, right, this is a tangent, right? And here obviously we have one line is like this, then the other line always have to be perpendicular to the tangent. When you have a collision between two surfaces where one surface is flat, like a wall or a pavement or whatever, right? Your line of action will always be perpendicular to the tangent, and then in that case, obviously the tangent to a flat surface will always be perpendicular to it. So regardless of how that shape look like, your line of action will actually always be like that because you have one surface that is flat. Okay, so again, E is always applied along here, right? So the final velocity of this guy has to be like that, but you're gonna take this component of it, right? And the initial velocity of this guy is like that, but you're gonna take this component of it because only in this equation, okay, in the coefficient of restitution. The rest is obviously the impulse. And there is a recording, on which I posted about this problem. So make sure you revisit this problem, especially for the exam, to freshen up your mind again. So make sure you do these, and make sure you solve this problem which I mentioned. Like you have this, right? And here we have friction basically changes as this block basically slides on that semi-dome, right? So as this guy basically slides down, your friction is going to reduce. So here you're going to integrate the work of friction. I'm not going to do it now, but I need you guys to work on it and then make sure you are familiar with that. Okay, guys, any more questions? If no more questions, then I think we're good. Okay, okay, guys, so I guess it doesn't seem like anyone has any question here, so I think we are good. And I'll see you guys on Wednesday again. On Wednesday, I will be posting the lectures again, and what I'll do actually, I'll also have these live classes on Wednesday. Okay. All right. Thank you.
But we have another class at 10. Can we do 2 sections separately?
Yes, 2 sections. This is what we'll do. There will be 2 sections.
Okay. Thank you.
Okay. You're welcome.
Thank you, doctor.
You're welcome.